Today I am going to take sixth lecture of Mat 303. In the previous lecture, we defined sine hyperbolic and cos hyperbolic, but for the real numbers. Today I define sine hyperbolic z is e raised to z minus e raised to minus z divided by 2, and cos hyperbolic z, that is e raised to z e raised to minus z divided by 2. The same definition, but z as a complex number means we define this as a complex variable. Now if we differentiate sine hyperbolic z, so obviously e raised 1 upon 2 is constant, differentiation of e raised to z is e raised to z itself, minus e raised to minus z, and differentiation of minus z will be minus 1, so we multiply by minus 1, and so this is cos hyperbolic z. Likewise, differentiation of cos hyperbolic z is 1 by 2. Differentiation of e raised to z is e raised to z, e raised to minus z is e raised to minus z, and we multiply it by minus sign, so it will be sine hyperbolic z. So differentiation of sine hyperbolic z is cos hyperbolic z, differentiation of cos hyperbolic z is sine hyperbolic z. And there are few results which we have already proved as a real number. Here as a complex variable, or for a complex number you have to prove this same. So you may go through up to 79, and we start with 80. Sine alpha plus I beta is x plus I y. You already have these notes, so you may have your statement of the example. So you go through from my notes, open that example, and I am writing the solution here. Therefore, sin alpha cos hyperbolic beta plus I cos alpha sin hyperbolic beta is equal to x plus IY. Now we compare both the real and complex numbers. So here we have x is sin alpha cos hyperbolic beta and y equal to cos alpha sin hyperbolic beta. Means real to real, complex to complex, imaginary to imaginary. Now here we have the first statement is x square upon cos hyperbolic square beta plus y square upon sin hyperbolic square beta. The values of x and y are there, so it is sin square alpha cos hyperbolic square beta upon cos hyperbolic square beta plus y square, that is cos square alpha into sin hyperbolic square beta divided by sin hyperbolic square beta. Now we can cancel out cos hyperbolic square beta, and sin hyperbolic square beta. So we have sin square alpha plus cos square alpha, and that is equal to 1. So the first result is obviously very easy. So we are going through the second one. In second one, we are having x square upon sin square alpha minus y square upon cos square alpha. So this is equal to, now we are having the values of x and y there. We just put it here and we find the solution, and that is sin square alpha into cos hyperbolic square beta upon sin square alpha minus cos square alpha sin hyperbolic square beta upon cos square alpha. So again we can cancel out both these terms. So here we have cos hyperbolic square beta minus sin hyperbolic square beta, and that we know very well that this is equal to 1. And though 80 is over, very simple, just use the formula to compare the real to real and imaginary to imaginary. You will find values for x and y. Just put it here. Obvious answers are there. Next, definition of convergence of sequence. So we are in a very early stage of convergence. So for that, here it's a convergence of sequence, and after some time there will be convergence of series. So what is sequence? Always keep in mind what is sequence. Sequence is a function whose domain is n. Sequence is a function whose domain is n. It may be real, it may be complex, it may be something else. And what is series? Sum of terms of sequence is series. So here we are talking about convergence. So what is convergence? As you know, if we start with 1, suppose it is 1 upon n, and you know that this is 1 and this is 0. If n is 1, it is 1. If n is 2, it is 1 by 2. If n is 3, it is 1 by 3. If n is 4, it is 1 by 4. And ultimately, we reach to 0. Actually, we are very near to 0. We never achieve 0. Because there is no value of n tends to infinity for which 1 upon n is 0. There is no value. But we are actually very near to 0, and though we say that limit of 1 upon n equal to 0, we are used to rather, limit n tends to infinity, 1 upon n is 0. What it means? It means that as n tends to infinity, 1 upon n equal to 0. But here I will explain you as we are going further in the study. But right now we are talking about the convergence of sequence. So here it's a sequence of complex numbers z1, z2, z3. You have to write dicto as I have given in written form in my notes. It is 81. Just I am capturing the core idea, main idea of that. Z1, Z2, Z3, all these are complex numbers. We say that this is a sequence as it is a function, as it is, whenever we say that it is convergent, if for given epsilon positive, there is n0 in n such that Zn minus Z is less than epsilon for n is greater than or equal to n0. And the notation Here used to by this. This is a complex number. This is a complex number. And this is definition of convergence of sequence of complex numbers. So what is sequence? Sequence is a function whose domain is n. What is convergence? If for each epsilon positive there is, and this is symbol of there is, and this is symbol of such that. There is means there exists. Such that means by using that way in mathematics. Now I request all students to learn the statement of 82 which I have given to you in notes. Just I am waiting for a minute. Just go through this from the statement of from my notes. Here Zn xn plus iyn and z equal to x plus iy. Limit n tends to infinity, xn equal to x, and limit yn equal to y, n tends to infinity. This double implies, actually this is a statement which we wanted to prove in double implies. So let's start with the first part. You know that this proof is in double implies. So we start with this part and we are going to prove this part. And secondly we take this part and we prove the first part. So here we have limit n tends to infinity, xn is x, and limit yn is y as n tends to infinity. Therefore, for epsilon positive, there are n1 in n, and n2 in n, such that xn minus x is less than epsilon by 2, yn minus y is less than epsilon by 2. I say this is true for all n greater than equal to n1 or say greater than n1, and this is true for all n greater than n2. This term is true for n greater than n1. This term is true for n greater than n2. You know that if we take the number which is maximum of n1 and n2, then this will work for all n. Therefore, for that we define n0 equal to maximum of n1 and n2. So if I say this as 1 and this as 2, then obviously you understand that for n greater than n0 implies 1 and 2 holds. Both these are holds, which both these are true. Therefore, xn minus x is less than epsilon by 2, yn minus y less than epsilon by 2 for all n greater than n0. Now if we start with Zn minus z, obviously it is xn plus Iyn minus x plus Iy simplified xn minus x yn minus y. I think there are so many ways to simplify it, but I am using the fact that triangle inequality, the first term, the second term. Now at this juncture, I used to ask one question, where is I? Just think it. Where is I? I think you are not answerable. You have no answer for that. I should say, okay, this is less than or equal to. Clear? Now, I is there. Okay? Yes, it is there. Now we can split this mod. Yes, we can split this mod. What is modulus of I? You know value for I? Is 0, 1. And therefore this is square root of 0 square, 1 square, and therefore it is 1. And though it is there, but invisible. And therefore it is there, but as its value is 1, therefore we should ignore it. And therefore this value is equal to epsilon, and therefore Zn minus z is an epsilon, and therefore this holds. Now if we start with the second part, okay, for second part, here limit n tends to infinity, Zn is z. Therefore by definition, for epsilon positive, there is n0 in n such that Zn minus z is less than epsilon. Now you understand that which type of idea we are going to use here. Xn plus Iyn minus x plus Iy. It's less than epsilon. What it means? What it means? It means that square root of xn minus x square yn minus y square is less than epsilon. I think you have this idea which way we are going to prove it. Therefore, xn minus x is less than or equal to mod of Zn minus z. This is Zn minus z. And yn minus y so for each epsilon there is n0 for which xn minus x less than epsilon. For each epsilon, there is n0 for which yn minus y less than epsilon. This means both these holds. And this proves the theorem. This proves the theorem. Try to capture the idea behind it. Okay? So we complete 82 and just I will take few minutes for today this lecture and I will conclude this lecture. Okay? We are going for 83. Limit n tends to infinity 1n cube plus I. As n tends to infinity, this value is 0 and this value will be I itself because there is no value of n and therefore obviously this is I. But what is it actually? It is 1 upon n cube and 1. It's a thing. It is 1 upon n cube 1. So, in R2, it is somewhere in the first quadrant, but it is very near to this y-axis, very near to y-axis, and y coordinate is 1. But as n tends to infinity, this value tends to 0. So, what is argument of 1 upon n cube plus I? As n tends to infinity, it is approximately 5. It is approximately 5. You understand? Try to open your mind, you will understand what I want to say. In 84, limit n tends to infinity minus 2 plus I minus 1 raised to n upon n square. So, in R2, this is minus 2. In negative x-axis, it is minus 2, 0. And this point is where maybe in this side or maybe in this side. If it is positive, then it is from this side. And if it is negative, then it is from this side. Means it is within the second quadrant or in the third quadrant. So argument of this, if it is from positive, then argument is pi. And if it is negative, then argument is minus pi. Okay, I conclude this lecture here.